All right, so what we're looking at today is module 3 of the series that we've already done. If you haven't attended, all the previous ones are available online. They're being uploaded to YouTube as we go. Today's module is Dante AES67 with PTP Protocol and Analysis. I'll explain in depth what PTP is, so if that's not something you've come across just yet, I'm going to explain it a lot. Before we go any further, I do want to say that this has been a very interesting subject to do training on, and there is a lot to know about this. We're not going to cover it. In fact, I think we'd probably be saying that we're scratching the surface of PTP. And there is a lot of reasons as to why that is. Partly, you do need to know about it as an AV person and understand it, which is what we're going to cover today in large. And as far as fault finding and those sort of things, we'll be able to do all of that. But the reality with PTP is it's a massive thing that spans across industries, and you can really, if you dig into it, there's a lot, and you can overwhelm yourself very quickly with how much there is. So moving on, introductions. As you'll probably know, I am Malden Grewitt. I'm the Technical Support Manager at JPro and Training Manager. And I'm an AV person, much like yourselves. I've been doing this for some time, and as you would have heard in the previous stuff, the networking part of everything is quite interesting to me. In particular, this subject is quite interesting because it hits close to a lot of older type technologies. You'll see the relation to it. And much like you, I'm diving into the networking stuff. I've dived into it for a few years now. And this training is intended to teach you those sort of things that I've learned and things that are going to be useful to you to know, but also to help you troubleshoot sites and those sort of things. So moving forward, these are the topics we're going to cover today. Digital clocking, what is PTP, PTP versions, PTP in relation to Dante and AES67, monitoring PTP, then some tools that I found that are really good. That was not meant to hop that forward. Sorry. Some tools that I found useful. So Dante Controller, clock monitoring, listen to AES67 seams and AES67 discovery with RAV2 SAP. So we're going to cover quite a few little things, fairly interesting stuff. I hope you find this topics really interesting. I'm looking forward to some Q&A when they come up, but we'll go through it. So precision time protocol. All right, diving into the deep end. So understanding digital clocking. Now, if you're not familiar with digital clocking, this is going to be a brief explanation on what digital clocking is in context of audio. You need to understand this because it makes it easier to understand the importance of PTP. For many of you, you already know how digital audio works, the conversion process and how everything moves from there, but it is imperative that you understand these concepts in terms of going forward, what the rest of this is going to mean and what PTP plays in this role. So looking at audio sample, you'll notice he has voltage and time. Basically, analog audio, as it comes into a system, it gets transferred from, let's say, a microphone from acoustic to analog to electrical, and that's defined in voltage and time. Voltage being a positive field and a negative field, kind of like AC, and the higher the wave, the more the volume is in some sense. There's a lot more detail to it, but the part that we want to understand is the digitizing of it. So how digital audio works is that as it comes in, you'll have seen that you get sample rates called 48 kilohertz, and you've seen bit def before. Bit def is like 16-bit and 24-bit. I'm not going to go into great detail with these sort of things because you can find that online quite easily, and this is not really the necessary to know PTP other than this one part. So what happens in digital audio is that as time passes, samples get taken at reference points. And what happens with one audio form, so let's say this is my DSP playing audio now, it's digital, it has these sample points, so 1, 2, 3 as an example. What happens is that as it gets distributed across a system, be it a digital audio system or a network or something like that, other devices have to play out the same waveform. And it uses the same references. So 1, 2, 3 in those areas there, it has to represent it again as 1, 2, and 3. What we want to grasp with this is the way this waveform looks and how it's going to play out is all defined by how these references are reproduced, how accurate they are. And if these are slightly off, things happen, which is what we're going to look at. So this is a common thing called jitter. Jitter is a very well-researched subject that you can look into, but if you want a very quick, I've experienced jitter. Jitter is commonly clicks and pops. So when a digital audio system starts to untangle or starts to go wrong, you get jitter. And for you in the AV space, you would know that as clicks and pops. Now, there's reasons why it's clicks and pops, which I might detail. But in reality, what happens is that these little samples that get taken on a stable system will represent perfectly. In other words, the waveform will be reproduced as if it was in its analog form. You can put it in that context. But if you have jitter, bad clocking happening, what you'll have is that where it had good reference marks, it's going to miss some points and it's not going to reproduce the waveform correctly. In other words, the little numbers aren't going to reference to the right place. So where we're talking about the waveform before being perfect, 1, 2, 3, and these exact places, jitter is the same thing, but where the clocking happens at weird intervals, in other words, there's an issue, and it causes this offset. And what happens is the waveform gets reproduced incorrectly. It's clicks and pops because depending on how it reproduces this, if you think of it as electrical, so if we think of digital audio being converted to electricity again, in other words, back to electrical form, kind of what happens in an amplifier or just before the speaker. The clicks and things you're hearing is that waveform being misrepresented wrong, but more importantly, because it jumps from one point to another point, it causes the electrical part of it to go from one reference to another very suddenly. In other words, not smoothly. And you hear it as clicks and pops on a speaker in the acoustic world, because from an electrical perspective, the speaker driver goes smoothly, operates as you expect. In other words, it flows in and out. And then if that misrepresentation happens, what happens to the driver is it goes from this point to that point suddenly. So it will just hop. That's that kind of pop sound you hear or clicks. So the driver violently moving to random intervals is actually clicks and pops. And that's because of how that waveform is being represented. So now that we understand that in a very basic form, we understand a bit of what this jitter can be and bad clocking can sound like. So a bit of back history. In the digital audio realm, we used to have, we used to have a master clock. A lot of you that have been in the audio space for some time will straight away notice that's a Big Ben from Apogee, the most popular common clock you get out there almost in the live industry and studio. Anyway, this device in the middle is the clock. And what this device used to do is align all these devices to play out audio at the same time using clock, word clock, or other mechanisms. But what we want to understand is that there was one central place that said, this is the current reference for 1, 2, 3, and 0 in time reference. And these devices would then follow that and play out at 1, 2, 3 at the exact same references. Ergo, this is kind of like a beating heart to an entire system, and this is keeping all other devices in sync at the same time. What I really wanted to illustrate with this is that you'll see there are different versions of this type of protocol. So from this device, it would go word clock to this direct out unit, MADI distribution unit, and then that would use MADI to go to the console, or AES EBU to the amplifier. And in the video space, you used to have LTC, which would supply to the video mixing console, and the video mixing console would do either 3G SDI or LTC or VTC to the cameras, and that would keep them in sync. Likewise with massive routers. And then this part is interesting to you from an AV perspective. is you would have LTC distributed to some sort of matrix router, and that matrix router would actually distribute time on HDMI. So even on basic things that you use every day, this has been there all the time. Your Apple TV to your HDMI, there is a clock that's running between the two to keep them in sync. So it's quite a integrated thing that has been there for some time. And unless you've dealt with live or broadcast or high-end studio stuff, you've never really been seen or exposed to some of this. I'm not saying you're not aware of it, but just being that it's around all the time. And one of the reasons that you're not exposed to it as much is because a lot of this is taken care of by devices automatically. So the HDMI to your Apple TV, they handle themselves doing that. So you don't see it, but it is happening with it. Now, that's the old or current. A lot of this is still current. You still work this way, but this is a very digital way of doing it. It's very hard to say that digital because the next one is exactly that. Now, moving forward, we've moved into this AV over IP world where we have lots of products that are relying on an Ethernet connection or a switch or a network connection. And what's changed is you have a master clock device, still remains. Something has to be the beating heart of the entire system. And it's using Ethernet cables and various protocols to transfer that clock system for you. And how that all works is that it distributes a clock signal over the network that's common. It's a network protocol that's used amongst other things, and it gets supplied to other devices through different means. All of these will either be running the same protocol, which is what we're going to learn about today, or something that's branched off from that protocol that's being used. I wanted to illustrate it this way again, because once again, you have a video encoder, an IP over video over IP product that is supplying clock to an HDMI device, and it's working through that mechanism. Of course, we're talking about a very audio thing, but it affects video because video also uses time sync clocking to play out frames on time. So your audio and your video frames play out in sync. That's clocking that's happening there. But more importantly, we need to understand that as much as this is an audio, it does affect the video side equally so. So this is what a network distribution system would look like. Some of you have probably never seen this particular unit here. It's just a Dante interface that's dedicated to clocking, but it happens. As we go forward, you'll learn how you have this running all the time, but you've not seen it just yet. So I've literally copied and pasted this particular thing with a few alterations because I wanted to word it perfectly to you. It's very detailed. But I am going to read it out, and I am going to read some things wrong. So if you didn't know, PTP is Precision Time Protocol. That is what PTP stands for. And this is what it is. To synchronize distributed clocks throughout a local area network, LAN, Network Time Protocol, NTP, and Simple Network Time Protocol, SNTP, are popular methods that are accurate to the millisecond range. However, for industrial networks, clock synchronization requirements need to be much greater. So in summary, just to give you a relatable thing, NTP is what gets distributed from your computer, or not distributed from your computer, distributed from your network, and is what syncs the clock on your computer. So in Windows, you would know that little clock that sits in the corner. That's using NTP to get its sync. And it's everywhere. NTP is constantly running across networks, and as something as simple as the clock on your PC, it's using NTP as the protocol. But what we do learn from that is that those two protocols are not high enough precision to be used for what we need. So moving on to the next part. The IEEE 1588 standard for Precision Time Protocol, which was first adopted in 2002 for automation and measurement applications, provides a method for clock synchronization with millisecond accuracy. PTP was also adopted under the IEC 61588 standard in 2004. Version 2 of the IEE1588 standard was retrofitted in 2008 to address telecommunications and audio-video bridging applications. So you can see as we move to the version 2 that's mentioned there, that audio-video is now part of it, but we also learned that PTP, and we learn this consequently following the next statement, is used on a lot of things beyond audio and so forth. So PTP is in demand wherever processes need to be synchronized exactly, such as automation and control systems, measurement and automatic test systems, power generation, transmission, and distribution systems, as well as telecoms. PTP is a clocking protocol used on a network like word clock was used on digital systems. It is the clocking system for most network digital audio systems and beyond. Now, what that really tells us is that PTP, the thing that we're about to learn, is used on way more than just audio or video for that matter. So it's good to know this because when you start Googling this particular topic, you're going to find a lot of information. And you need to understand that PTP is not specific to audio and video. It is a common protocol used for a lot of things. But what's really interesting to see is that it's such a precision clock system that it gets used on automation and a lot of really, really important systems. And this is why when you start looking this particular topic up, you're going to find a lot of information. And that's why I said we're just scratching the surface, because in the audio realm, we don't need to go that deep, but there is a lot that it can do. And it's also understanding that you're going to find some misleading information that could make you think something is not appropriate for the application. One of the examples I can give you is that if you look up a Cisco N9200 switch, which is a very nice switch, you're going to find that it does not support PTP, or at least the documentation reads that the 9300s support PTP. If you misread that and you assume that means that switch will not work with what we're about to discuss, Dante and AES67, you would immediately think, I can't use that switch. However, what it's referring to is where it's being used as the clocking system or for other network stuff, not related to the audio side. So if I was running a massive automation production line for a car manufacturing plant, the 9300 that supports PTP would be a consideration, whereas the 9200 wouldn't because it doesn't support that level of PTP. Now, Dante and AES67 and the standards that we're going to learn about, they don't need switches to support that level of PTP. So that's just something to be aware of. And as you dig deep, you're going to find a lot of that sort of things being mentioned. So moving on. How does precision time protocol work, or what is the basics of what we need to understand? Well, basically, you have a master clock, a device on your network that is supplying the clocking system and saying this is the current time of day or current sync. And what that device does is it sends off a sync message and the slave clocks receive it. And then they start setting themselves up to work with that. Now, what actually happens with all of that in the detailed thing is it sends the sync message, the slave device receives it, and then the other master clock sends a follow-up message to say, this time I sent at, let's use 1 millisecond, then this time it receives it at 2 milliseconds. And what happens in that time interval is it works out the network latency and delay, how long it's taken for that packet to arrive. So now it knows between from T1 to T2, it can now determine that there is a 1 milliseconds latency that it has to add on to the clock reference it gets. A very simple way of thinking about it. If I told master clock switch said it's 1 o'clock, right? And then this switch then receives it at 2 o'clock. And then, but it received the 1 o'clock message. Now understand that this is sending out a time, 1 o'clock. Receives, but it receives it at 2, but it receives 1 o'clock. For this switch to 1 o'clock would defeat the whole purpose of the system. So what happens is that it goes from 1 o'clock, receives it, it says, oh, you said it's 1 o'clock, okay. And then it sends another one and it says, now it's 1001. And it's like, okay, so the latency is 1 millisecond or 1 second, whichever example there is. And then it sends another one saying, well, I received this at 1002. And then it transmits it to the master switch. And then the master switch sends another one and says, well, it's now 105. And with that, it works out the network latency and what time it needs to sync up to. So instead of it just saying it's 1 o'clock and it going it's 1 o'clock, it's actually doing a calculation in the background to determine network latency and other variables that could play. And then only on the last point does it receive this. These physically appear as packets on the network. So you actually do see these transmits. So if you were to Wireshark a PTP protocol, you will see the sync follow-up, the delay request, and the delay responses around that. But what we understand at this point is that we're currently referring to switches, but these can also be devices. So if my Dante master clock sends out a PTP clock and it's received on my Dante IO unit, slave unit, then it's using the same methodology to work out what the sync is for the network. Now, there's a thing called BMCA, which is best master. I'm supposed to write these things down. I forgot what BMCA is. Best master something. I'm really sorry. I had that somewhere safe. Give me a second. Base master clock algorithm. Sorry about that. So what that is this is how master clocks are elected in a system. And you might wonder, well, I've plugged Dante stuff in and it just works, which is true for the most part. But there is something that says, okay, you're the master clock. And BMCA is part of the PTP protocol that does this. So what happens is that when you power up a device or you restart a device, it goes into listening mode. And then it announces a message from the beta master. And then if it doesn't receive any response, then it will elect itself as the Grand Master. So what is that? You will see an announced message fly over the network asking, is anybody the master around here? Should I be listening to you? And if it doesn't get anything, it will elect itself as the master. Likewise, if it announces and then the master says, hey, I'm the master, then it will tell the device to switch to slave. This is basically how the communication of master and slave clocking systems work on the network within PTP. Now, down here is just some things I wanted to show you, but one of them is this MAC address. So what happens with BMCA is that if it finds two devices that can serve as the master, it uses MAC addressing as the final part to determine, okay, you're the master. And part of this is what you'll see is as it goes through this, it chooses the master. So it chooses, so this is if nothing is forced as master, if there's just a magnitude of devices. It goes by priority, so it looks at the PTP packet and sees, okay, well, you're a priority something, so I might use you, you're higher priority than me, the class, the time source, the variance. This is where it plays in. This does look at the PTP messaging that's happened and the latency on the network and how accurate the latency is to elect who becomes master. Now, that is the process, and if as I said, if there are two good options, it will use the MAC addressing as part of it with this. Now, PTP versions, there are two types of versions you get, PTP v1 and PTP v2. PTP v1 is common on Dante. That's the one you find on Dante. And PTP v2 is what's common on AES67 amongst a lot of other standards out there. Now, to just briefly understand them, you can go for a long argument between the two. But there is some basic understanding that you can just use on it. When PTP v1 came out, and Dante in this instance, that was before PTP v2. Obvious, I know, but there is a thing to understand with these things, is that PTP v1 came out quite some time ago, and Dante came out about a year after that. And Dante used PTP v1 first. Then PTP v2 came out a year after Dante came out, and it was still in its infancy. I mean, if you look at AES67, it's taken a long time for it to get to where it was or is now. You use it a lot nowadays, but AES67, I believe, was announced in 2007, or the intention of something along those lines was done then, and it's taken that long to get there. So what I'm trying to explain is, why does Dante use PTP v1? So Dante uses PTP v1 because of when it came out. This is the first reason. For backward compatibility. So PTP v2 is not backward compatible with v1. In other words, if you're running PTP v2, you can't run or clock PTP v1 natively between them. There's a system that you'll become aware of as we go, but they weren't backward compatible. In other words, if that packet was flying on the network, a PTP v2, the PTP v1 device can't just use PTP v2 naturally. It is a process that would have to happen. So Dante uses PTP v1 because of that, and then also PTP v1 is a lot simpler because it's an older standard, but it means that it will work 99% of the time. Whereas PTP v2 has more features that make it more complex. It's more designed for very large automation, industrial automation systems. And it has a higher transmit. In other words, it transmits PTP packets higher or more accurately than PTP v1 does. Now that will sound like, oh, I just want to use PTP v2 because it's way more accurate, best thing ever. However, more packets on the network equals more traffic equals more load. And when you're trying to do this on a everybody can just use a product, using PTP v1 is easier because it will run on any switch, even 100 meg switches or 10 meg if you go that far. And it will work because it's not pushing out as much packets. And Dante has rightfully said that the PTP v1 standard sends enough packets out that it's not a problem for digital audio in this case. So what we learn is, as great as PTP v2 is, it is better, but it's not necessary because PTP v1 functions fine. And there are thousands of Dante systems in the world that run on it, and they haven't had issues. So we understand there's two standards. But what we can also grasp from this is that there is that there are other standards underneath PTP too. So AES67 is the most common one that you'll be familiar with, but QLAN started on PTP v1 and then moved to PTP v2. I'm going to stumble my words quite a bit. And with that, SIMT and a few others are running v2 now. So be aware, Dante runs PTP v1 and PTP v2 is run on pretty much most of the other standards. Now, as I said, it's not backward compatible. So looking at Dante and AES67, if you've used Dante Controller recently, you would have seen there's been a change in naming. Namely, there's a primary v1 multicast and primary v2 multicast, and then there's secondary and that v2. What this is v1 is PTP v1, and v2 is PTP v2. How this works and how you're able to interface AES67 and Dante together using this clocking protocol is that you get a thing called a boundary clock. A boundary clock is a device that's capable of transmitting two or more types of PTP packets. In other words, instead of just being able to receive PTP or transmit PTP v1, you're able to receive PTP v1 and then send out a reclocking of the same clock information, but in PTP v2. Now, when you look at boundary clocks on the web, you're going to find a lot of networking stuff because this protocol is used on a lot of things. But how Dante works with it is that all of Dante's systems will rely on PTP v1, the first one here. And then when you implement a boundary clock to clock AES67 streams from Dante, so forth, or whatever it might be that you're interfacing between the two, a boundary clock is deployed, and that will then allow the packets to move between them. In other words, this Dante system can clock that system. And you'll see here leader and follower, e.g. master, and follower, meaning that it's clocking to PTP v1 in that scenario. It's crucial to understand this because where we had one clocking system, we now have two clocking systems. So whenever you do an AES67 to Dante system, there is actually two master clock systems and they're clocking one another. Well, the master clock of the one is clocking the other, and that's the other master clock. So at this stage, we actually end up with a split. Now, something that you'll see later, I'll demonstrate it to you, is that you don't have to use the same device to do the boundary clock. So as much as this shows this is the leader and the follower, I can actually mingle it around and have that one be the leader and that one be the follower. And I'll show you what that looks like later. So at this stage, we understand that the boundary clock can be used to go from PTP v1 to PTP v2, but it also gets used for moving clocking systems between. It reclocks the system. And this is where we move into the next part. So transparent clock versus boundary clock. So a boundary clock, the switch acting as a boundary clock will use PTP v2 to update its own time and apply that to the packets that it sends. So of course, when we did the Wireshark, we understand everything's packetized. And what we see here is that the boundary clock takes the packet and then reclocks it and sends it out again. Seems really obvious. A transparent clock will calculate how long packets have spent inside of itself and add correction for that to the packets as they leave. In that sense, the switch becomes transparent in time, as if it's not contributing to the delay in the network additive. So the reason that these two are mentioned is that when you start Googling or looking up boundary clock, you're going to find mention of transparent clock. Now, we just saw that AES67 relies on boundary clock type systems. And a transparent clock system is something you will find probably in the future get implemented more into our audio space, but PTP can use these two types of systems. We typically stick to the boundary clock. I wanted to make you aware of transparent clock, that one day if it does come into play, you understand the differences. And really what we see here is that a boundary has to take the packet, take it apart, and then reclock out. So it reads the data, and then it sends out a whole new packet. Takes more processing, takes more time. The transparent clock simply just adds the new counter clock to it. So it's as if it's just adding a little bit of data. In other words, it's less intensive. Really detailed, overboard, but good to know. So PTP in relation to Dante and AES67, time adds up. So with this syncing thing, as we're sending messages off on the master clock, this is what I showed you before. You'll see that this time variable gets worked out to how much delay there is. I wanted to show you this to understand that the larger the network, the more time you're going to add, the more latency. So where you place your master clock system and how far it needs to run down to the final point adds latency. And remember, this is for the whole system, so it's going to clock down all the way to the end point. So what we see here is a grand master, a slave, a boundary clock, and then another master, a slave, and then an ordinary clock. Let's put this into perspective. Grand master, my main clock. So if I'm using a blue 806 as my master Dante clock, that would be that. And then my slave device would be, let's use SVSI. So SVSI is a slave unit, and then it acts as the boundary clock. In other words, it's reclocking for PTP v2 to do AES67. Then it retransmits out the packets as the master that will clock all the PTP to. What we want to understand is that as you scale through this, you're adding time. You're adding latency to that clock, and it eventually will go too far. In other words, it cannot reliably use it. So where the boundary clocks become really interesting, and I am curious to know how many of you would be interested in a DDM class, Dante Domain Manager class on this topic in particular. But where boundary clocks get used in DDM, which is an optional Dante thing you can deploy, is as you create subdomains in DDM, in other words, smaller Dante systems, on the same network. In DDM, you can break Dante into smaller systems. It creates a boundary clock. And for every boundary clock, it means that it will be able to receive those packets and reclock it out through that new system. So where you might be pushing the restraints of Dante by going above 400 devices, for example, and you start having PTP issues, using boundary clocks and subbing systems into smaller domains and having them less reliant on that one master device distributing all the master clock out creates multitudes of submasters that you can use. Where it gets used in DDM in a very interesting way is that you can use these boundary clocks to do GPS clocking so that you can separate Dante systems by land or by very large distances. So if I wanted to do a DDM system that operates between New Zealand and Australia, a Dante system, I can use GPS clocking and I can transfer Dante over a VPN or some sort of private network. And no matter how long it takes, because these are using GPS to reclock the packets, it will remain in sync and will probably play out. This is a very complicated system, and I know it might be very exciting. But in essence, because you can reclock things using boundary clocks, this helps do that. You can achieve it. Right, PTP settings to be aware of. So inside a PTP setting, there is a QoS setting, obviously. QoS, if you're not sure, is quality of service on networking. And how that works is that when you have packets on the network, it needs to prioritize certain things. You can use QoS to say this packet or this information or protocol is more important than this and this and this. Some of you have already probably played with QoS quite a bit and understand it, but essentially means that when a switch is receiving data at a high rate, it will prioritize other packets over others by using the QoS system that you set up. Of course, we just think, oh, well, I'm just going to tell Dante to be highest priority ever because I want it to be super reliable. However, Dante's packets are broken up, and AES67 and many others. So understanding that for Dante to work, you have the audio stream, and you have the PTP stream, and you have the discovery stream, and a few other ones along with it. Those are all separate packets. And QoS applied to that, you can't just jam them all into the same thing because that kind of defeats the purpose. The number one priority for anything that runs audio is PTP. So on a switch or a network, you want to prioritize PTP as the highest reliable packet that has to come through. And it's one of those settings that you can set on your switch. So it's naturally always defined by the manufacturer. So Dante and AES67 give it that priority. And when you enable QoS, it's going to put it as the highest priority. But the thing to understand is this is why PTP is so important to know, is that when those packets don't come, we're going to get dropout. We're going to get clicks and pops. So we want to prioritize them that they arrive all the time. So I get packet after packet after packet. And QoS is the method that's used to do that process. So by using QoS, you're ensuring that you receive those packets all the time. Then on PTP v2, you get some domain settings that you can use. So PTP v2 being a newer standard, it has more things. And a domain within a PTP is a segment of clocking. So you can have a domain 0, and then you can have a domain 1. And the differences between the two is that domain 0 will just be for anything that subscribes to the 0 PTP clocking packet. And if you have something on domain 1, then it subscribes to the clocking packet for domain 1. Now, just for reference, what we were talking about before, these would be two different domain numbers. So in this one, you would set a different domain number. So instead of using 0, you would set that to 1 and this to 2. And then these devices will clock off of those and not get confused. In other words, you could run two different clocking PTP standards and devices. This is getting into super geeky type stuff, very broadcast level only. You will not use it in your common AV installation, but be aware it is there. And what I wanted to highlight is that Dante and AES67 use D0 as the default, and SMPTE, which is a more advanced version of AES67, uses 127 and can change. And in other PTP v2, specifically with SMPTE deployment, you can define a second clocking system as a failover. Again, this is very broadcast level stuff. You will not necessarily play with this, but be aware because in the future these things will come into play. The more we become AV over IP focus, the higher these sort of things are going to start playing. Now, moving on to something that is useful for you, a piece of software that will help you. So PTP Trackhound is the software that you can use for free that will allow you to track this stuff. Now, this is where we're getting into practical use. So I'm just going to bring that up for you. Over here, we have that software installed on my PC. I will send you the link right now on the chat so that you guys can grab it eventually. Obviously, don't expect you to install it right away. PTP Trackhound is an application that is made by Merberg brand. They do broadcast level PTP management and that sort of stuff. But what this application allows you to do is see the PTP information. Now, you can Wireshark all of this, but this is way more useful for you to see. So what you're currently seeing is not much. I'm just going to run you through these three at the top. You have the what protocol you're monitoring, port. So here I can say all my ports, or specifically I'm using port 3. Then you can use the protocol, IPv4, IPv6, or Wi-Fi. These two you're not really going to play much with. And then domains. Now, remember I told you about those domains. So in here, you can choose which domains is visible to you. And I'll give you the practical version of this now when I run this. You can also then say which messages you want to see, and you can choose devices. Over here is where you hit start and clear it. And then some of the settings and preferences are here. When you hit start, it's going to start collecting all of those PTP messages. So I'm connected to my network. I have an I have a Cisco SG350 switch, and I have a few Dante devices on my network. And what we're seeing here is all the information about PTP. So over here, I'm just going to pause it to stop the chaos. You can see it's collected this. Now, this is as if it was Wireshark. So I can see all this information. You can also see it in Wireshark. But what you're seeing here is the sync and the follow-up. So it's showing me the sync, the follow-up message, the sync, the follow-up. And what I would be looking for is, for example, sync messages going out, follow-ups failing, issues like that happening. When you click on any one of these, you'll see this populates down at the bottom. And in this window, you can see the raw data, same as Wireshark, and you can see the destination, source IP, you can see the IP addresses that it came off of, time to live, a lot of information. You can also see the clocking, the multicast packet. So PTP on Dante is using multicast. You can use unicast. And equally so, AES67, same concept. You will see multicast PTPs for AES67 and those sort. What I am able to see here is the multicast address. So if I had multicast blocking, for example, I wouldn't see that, or I would not see the message. So that would be a straight indicator that there is a problem. Equally so, if these packets never arrive to any of your devices, your system is not going to work. Or if you have clock instabilities, this is going to help you find what's going on from that perspective. Over here, you're able to see the UDP also and the PTV. So I can see this is PTP v1 is the protocol I'm using. And there's quite a bit of information around this. So I'm able to then look at each one of the packets. Now, this is a bit of a geek out because this is a lot of information that's super useful to someone that's really trying to fault find something. And you can also see the device, the address, and so forth. Why does all of this matter will become more obvious when I enable AES67. What I can also see on this side is the grandmaster. So I can see that this is the grandmaster. It's my alternate device, and it's that IP address, the port I picked it up, and so forth. And I can see the information about how that's operating and what it is doing. So that gives you quite a bit of information on that. What you can see then also is if there are any faults and errors. So quite a bit of information, useful, but let's put it into context because you need to understand why would this at all be useful. So moving up to Dante Controller, I'm just getting it to boot up. So here's Dante Controller. We can see DSP is my main device, which will correlate to that IP address on there. So that is my grandmaster, and these devices are the ones slaving to that grandmaster. Now, as I said, where this will become more interesting is if I was to AES67 something. So I'm going to go to this Avio adapter, and I'm going to enable AES67. Yes, it needs to reboot, so obviously it's not going to take effect straight away. And once that device comes up, the AES67 stream, we'll see it pop up here. So I'm going to run this again. Currently, we can see there's a grandmaster. And there we can see a slave. And if I go back to Dante Controller, you'll see underneath clock status, leader, and listening, and pre-leader. So it's done that whole election process and leader. So now it's the leader of the V2. Notice what I've done is this is my main Dante device, and I'm using that to reclock the V2. As you get into this, you need to understand that if this device fails, my AES67, my PTP V2 network is going to go into panic mode. That's why knowing that these two are actually linked, but if one fails, you have a big problem, is important. As you start playing with AES67, QLAN, many other standards, and you're mixing it with Dante, understand that that bridge is a small link between the two that's clocking the two systems. It's very reliable, as I'm sure none of you would probably tell me that I've had it fail all the time. But be aware that whatever you're electing plays a role, and the switch link between this plays a role. So if I had a switch that's interconnected between that and that, in other words, this device is on switch 1 and this is on device switch 2, and the link broke, it could create havoc because I've unlocked the clocking system. So where this is viewable, as you'll see here underneath the boundary clock, there's an alternate device, and that is the unit, and I can see that that's clocking that system. So if I dig deeper into the whole thing, you'll see here PTP V2, and if I hop over to here, PTP V1. So this allows me to see how many masters. Why is that interesting? Next time you're on an AV system that has AES67 and Dante, open up this tool and look how many clocking systems you have. Because we're working on a very small scenario right now, which is my Dante and in a small switch context. If I was running RTP streams, which is very common for some cameras on the market and that sort of stuff, you would see they have their own clocking system. RTP also relies on PTP systems. And you can notice like instabilities or issues through that if you run into any. But you'll actually realize that your system is tied up with these clocking systems. In other words, these are my master clocks, and these are the ones I'm relying on to handle everything. So what will be of interest is if you open this up one day and you see 10 master clock systems, that's a very inefficient system, and it could raise concerns. You'll notice over here on the side, I'm just going to pause that, that I've still got all this packet data. If I run down to the bottom now, you'll see there's more messages available. So sync, follow-up, these are V2 messages, sync, follow-up. Notice the announce message that I spoke about, which is part of the choosing the master. There's the announce stage, and you can see this going through. Why all of this is of interest is that if you're Wiresharking PTP issues, you need to know that you're looking for a sync, a follow-up, and so forth. If one of these doesn't happen, you're going to have problems, or if your network's blocking it or something's happening. So that's PTP Trackhound. There is definitely a lot more that it can be used for. It is a very broadcast application. In other words, it's for very serious PTP deployments. I would say if you're going above 50 devices on Dante and you're mixing with AES67, this is when these tools need to be looked at. If you're above 400, you need to open this up and start looking at how you're handling. And if you're mixing multiple things that work with PTP, you need to look at how that clocking systems work. Single beating heart, if your heart stops, you're going to have issues. In other words, it's going to involve clicks, pops, audio not working, video dropout also, because PTP is part of like RTP streams and those sort of things. So that's PTP Trackhound, useful little application. What we're going to look at now is Dante clocking monitoring and so forth, so a few other little tools. So Dante Controller clock monitoring. Now, when you open up Dante Controller, you would want to look at how that clocking system works. So what you have here is what you've seen, is you've got leader and follower, but what you're looking for is this down here. So when you click on this, this is normally where we see those mute error failures and those sort of things happen. Just for interest's sake, one of the reasons you'll have that mute thing happen is if PTP is not sustainable, it will cause it to mute. When I go into here and select a device, this is representing PTP. It's showing you how the clocking system is working, how much it has to delay by, and how well it's functioning. If this drifts past a certain point, you'll see devices mute and you'll lose audio. So again, why PTP plays a big thing is that you would have had that happen to you before. If this starts going haywire and your PTP packets are freaking out, you will see it happen on here and the device will mute on the network. And opening up something like Trackhound and those sort of applications, they'll allow you to see that happening. If I go over to here, I can see the difference, right? So this device, this little Avio USB that's sitting down there versus my PC that's running DVS, notice the time variance to try and align them in sync to one another. And then with the DSP, because the DSP is my master clock, it has almost none. So you can see how that latency is playing in role there. For interest, because we're looking at Dante, I just wanted to make you aware that Dante uses these multicast address 224.0.0.129 for its BTP. If you open up Wireshark on a Dante system, that's the package you're going to start seeing between these. And then the ports are 319 and 320. Because it is a multicast, if your switch has got poor multicast deployment or is struggling to handle multicast, you're going to notice it because the clocking system relies on that part. Moving forward, this is a very useful tool. I hope this is an eye-opener to everyone that uses AES67 and Dante. Probably most of you might already know about it. There is an application called Rev to SAP. It's this. Now, all of you would have seen this blue line before on Dante Controller at some point, which is when an AES67 stream becomes visible for Dante. And some of you might have had that aggravating thing that happens where you don't get that packet coming through. In other words, you can't see it. Rav to SAP helps you do that. So Rav to SAP is an application made by Ravinia. They're a broadcast audio transfer standard. And what it does is it allows you to see the SAP details and so forth, but it allows you to force things through. So when you first open it up, you just hit order, and it will push an SAP. I'll explain what an SAP is now. And what that'll do is it will basically push the subscriptions so that you'll see it on Dante and it will come up at that time. So if you've ever had that annoyance, Rav to SAP, that's the application. I will post the link to download. Again, it's a free program, so you can just download it. It's a trick more than anything. I don't think they intended us to use this for Dante because Ravenna's competition. But rolling into something of interest is, what is SAP? So SAP is a Session Announcement Protocol. What that does is whenever you start an AES67 stream on a network, it announces itself and says, hey, I'm an AES67 stream. This is my stream. And then it gives an SDP. I'll explain SDP now. That SAP protocol, if that is blocked or it can't come through or it doesn't arrive at your PC, such as Dante Controller, you will not see these AES67 streams come through. So where Rav to SAP plays in is this application finds them better than Dante can, and it allows you to push them onto your network or your computer or to discover it. So it's actually just re-announcing the SAP. From your computer, and Dante Controller picks it up easier because it's coming straight off your computer and it works quite nicely. Cool tool, useful if you want to play with it. But what I mentioned was SDAs, so SDPs, it's SDPs, Session Description Protocol. So this is an AES67 thing. And what happens when you do a SAP is it then has an SDP attached to it. The SDP carries the information about that stream. Now, as you're all aware, AES67 is a bridging protocol. It's not intended necessarily to be a replacement for Dante. It's intended to bridge from Dante to Ravenna or Dante to QLAN or something like that. And what AES67 does at that stage is it needs to release a file that tells you this is what it is, right? This is what I am, so that the other protocol will understand it. And that's an SDP, Session Description Protocol. So when you establish a link between your audio and another device, so Dante to AES67, it does this passing through data. And inside the packet, you'll see there's a version, the origin, in other words, the address it came from, the session name, that's normally the device name. You'll see that's the same as my Aviol. The multicast address that's been used by Aviol. The device info, so this is Dante. If it was Ravenna, it would say Ravenna. The audio, so the port that's being used, the type it's using, RTP, so the media name and transport. 2 channels and their names, so the channel names and the receive only session, the sample rate, the bit depth, channels, and then the clocking reference information, who's the grand leader and who's the standard. So it passes all of that through. A lot of information, but essentially all of this is how your AES67 session is established and how it works. So if you're missing pieces of this information, you would run into a slight problem. Now, where RAV to SAP helps is that you would have seen when I double clicked on this, it brings that up. I can see all that information. So just to correlate what you're seeing there is if I go to Dante Controller and I open up this little Avio, you'll see that underneath here, there's a multicast packet. That's the address that you see, the port, the channel names, that's all that information that's being pushed. If that information is incorrect or you're struggling to work with it, you'll want to see this information and work out what's gone wrong and how to deal with it from there. So that's RAV to SAP. Listening to AES67 streams, another useful tool that you can use, a small application that's called AES67 Stream Monitor. Again, these are just useful little things that you can use. Is a little application that you can run on your computer that will discover AES67 streams or those multicast addresses, and it will allow you to listen to them. So you'll see nothing's coming up, so I'm going to use my RAV to SAP and see if I can get this to come up quicker by clicking on things. There you go. And what this allows me to do is if I click on this, now I can listen to these individual channels. You'll be able to see the details of it. But more importantly, in the settings window, I can change what sound card I'm using to listen to them. So if I was to choose, this is my PC monitor, I have no idea how loud this would come out. It won't play anything, luckily. That will play that AES67 stream on my PC now, and I can listen to it from there. So useful tool if you're trying to figure out what's wrong with AES67 streams. These 3 tools will enable you to do those sort of things. Again, I will post a link to that little application. It's also a 3.1 that you can happily download. Great. That's it. I realized this was quite a very detailed session. It went through quite a bit. I hope it was helpful. In reality, probably rewatching this again will help make it a bit more understandable what everything I was saying. But the crux of it is that PTP is a clocking packet. It clocks your entire AV system, and there's 2 different types. And you need to be wary of how that's operating on the network. If there's any interference with it, any issues, you would run into problems with your system, and it could explain clicks and pops, issues with Dante systems, issues with AES67s, and video systems at the same time. Treat it as if it was a heart. It's imperative that it works. It's important that you know about it, especially as we go more into AV over IP. I feel when I dived into this that there is a lot you can learn, a lot more than I have shown you, but this is enough for this particular space of the industry. And I feel that you should be aware of it. And going forward into the future, we're going to use this a lot more. And if you look at a reference of what intense PTP systems will be, look up broadcast systems that use PTP. it's much more detailed there, and you can even use switches, network switches, to clock systems. So instead of relying on a single device for the Dante, a DSP, or something like that, in the broadcast realm, you actually get one dedicated PTP clock systems that are very expensive and very high end. And in the same space, you can actually have switches that are acting as the transparent clock, boundary clock, and master clock system. As we start indulging in larger systems above the 400 count, these things will start playing a very big role. And as we grow into more AV over IP and more devices are relying on PTP, we will find that these technologies are probably going to start coming down into our AV space that we're dealing with.